In this lecture, we want to understand the concept of relative velocity. We start with the most general case of relative velocity between 2 points in space, and we extend it for multiple points. Then we will learn how to deal with the relative velocity between 2 points, depending on whether they belong to the same rigid body or different rigid bodies. And finally, we will see a couple of examples. Let's start with the concept of relative velocity between 2 points. In the most general case, imagine we have 2 points in space, point A, whose velocity is VA, and point B with a known velocity of VB. The relative velocity of B with respect to A can be described as velocity of B minus velocity of A. If we consider a common origin for the velocities, known as OV, then we can bring both velocities to this point. Velocity of B with respect to A is this vector from the head of VA towards the head of VB. By solving for the velocity of point B, we obtain a more practical form of the equation. This new form implies that the velocity of a point can be described as its velocity relative to a reference point plus the velocity of that reference point. This relative velocity plays a key role whenever we want to establish a connection between a point whose velocity has been demanded and a reference point with a known velocity. Next, we want to extend the relative velocity formula for multiple points. So far, we understood that if we have 2 points with velocities VA and VB, velocity of B with respect to A is VB minus VA, a vector connecting the head of VA to the head of VB. Let's take into account a third point, M, with velocity Vm. In the right-hand side of the equation, we just add and subtract Vm. Let's make a rearrangement. Velocity of B minus velocity of M, and we put here. Similarly, we put together velocity of M minus velocity of A here. We simplify VB minus Vm to velocity of B with respect to M, which is a vector connecting heads of Vm and VB. Likewise, we replace Vm minus Va with velocity of M with respect to A, which is a vector connecting heads of VA and Vm. Let's highlight what this equation implies. Velocity of B with respect to A is the summation of velocity of B with respect to M and velocity of M with respect to A. It's like canceling out M with M and having B with respect to A, the same as on the other side. Now let's consider additional points such as N and P. Following the same pattern, we can extend velocity of B with respect to A to the summation of velocity of B with respect to M, velocity of M with respect to N, velocity of N with respect to P, and finally, velocity of P with respect to A. And again, it's like canceling out M with M, and then N with N, and finally P with P, resulting in B with respect to A, in agreement with the other side. So this is how a relative velocity can be equivalently extended to a sequence of consecutive relative velocities. Now, let's explore the relative velocity between 2 points when they belong to the same rigid body. Imagine we have a rigid body like this, and points A and B belong to this body. Along the straight line between A and B, they are not allowed to have any relative motion, because otherwise the body might get bigger or smaller and can no longer be assumed as rigid. Therefore, the only possible motion for B relative to A must be perpendicular to the line connecting them, which has to be a rotational motion. As a result, the relative velocity of B with respect to A is perpendicular to AB. And considering the angular velocity of this rigid body as omega-2, the velocity of B with respect to A can be formulated as the cross product of omega-2 and AB. The next scenario happens when the points in relation belong to different rigid bodies. Here is a common example. Imagine we have a rigid body with number 2 which contains a slot, and this pin which belongs to body number 3 has to move along the slot of body number 2. If we look closer at the pin, we can consider a point P3 belonging to body 3 and a point P2 belonging to body 2. Point P3 moves with body 3, but its so-called footprint P2 stays with body 2. Let's move back to the instant under consideration. Points P3 and P2 are instantly at the same position, but they have different velocities. Therefore, there's a relative motion between them, which can be described by velocity of P3 with respect to P2. This concept is known as the relative velocity of a point with respect to its footprint. More precisely, the relative velocity of a point of a body with respect to its footprint on another body. The direction of this relative velocity is along the slot, and during the motion it always remains tangent to the trajectory. Let's have our first example and practice how to apply the concept of relative velocity and the formulations we have learned. In this system, we have a link 2, which is pinned to the ground. Then link 3 is pinned to link 2 at point A. Finally, link 4 is connected to link 3 at pin B. And point C is located at the other end of link 4. We have all the dimensions, including the location of support O2 and the lengths and angles of all the links. This system has 3 degrees of freedom, and therefore 3 pieces of velocity information have been given, including the angular velocities of all the links. We need to find the velocities of points A, B, and C. Let's go for the solution, starting from velocity of point A. The angular velocity of link 2, omega 2, has been given in this direction. Therefore, velocity of point A is omega 2 times the distance from O2 to A. So we have the magnitude, and the direction should be perpendicular to link 2. Considering an origin for our velocity diagram, we can bring the velocity of point A there. Next, for the velocity of point B, we can relate it to point A, whose velocity has been already found. So, velocity of B can be formulated as the relative velocity of B with respect to A plus the velocity of A. Let's look into the velocity of B with respect to A. Points A and B belong to the same rigid body, link number 3. And we have the angular velocity of this link as omega 3. So velocity of B with respect to A is formulated as the angular velocity of link 3 times the distance from A to B. From there, we obtain the magnitude, and the direction is perpendicular to link 3. Next, we bring it to the diagram. It should start from the head of the velocity of its reference, point A. As this relation suggests, the velocity of B is the summation of the relative velocity of B with respect to A and the velocity of point A. As a result, this vector represents the velocity of B, whose magnitude and direction can now be measured. Finally, for the velocity of point C, we can relate it to point B because both magnitude and direction of velocity of B has been already obtained. Since the angular velocity of link 4 has been given as omega 4, the magnitude of velocity of C with respect to B can be written as omega 4 times BC. Here is the magnitude, and the direction is also known because it should be perpendicular to link 4. Next, we transfer this relative velocity to the diagram at the endpoint of VB because it is relative to B. According to this equation, the velocity of C, about which we didn't have any information, can now be obtained as the relative velocity of C with respect to B plus the velocity of B. Here is how we obtain the velocity of C. Then we can measure its magnitude and direction. Now let's highlight a couple of remarks. Remark number 1. Absolute velocities, like velocities of A, B, and C, they originate from OV. But that's not the case for relative velocities. A relative velocity should follow the velocity of its reference. For instance, velocity of B with respect to A follows VA, and velocity of C with respect to B continues from VB. Remark number 2, we could look at the velocity of C in a different way. It could be illustrated as the summation of velocity of C with respect to B, velocity of B with respect to A, and velocity of A. It's like canceling out B with B and A with A, resulting in C, which is in alignment with the other side. In the second example, we want to practice how to deal with the case of relative motion between separate bodies. We have a body number 2 sliding on the ground, and link 3 pinned to the slider at point A. Finally, slider 4 moving along the link. And point B located at the center of the slider. Dimensions have been given, including the location of point A as well as the distance and angle of AB. Since the system has 3 degrees of freedom, 3 pieces of velocity information have been given, including velocity of point A, magnitude, and direction. Angular velocity of link 3, and the relative velocity of the slider along the link, magnitude and direction. We need to find the absolute velocity of point B of slider 4. For the solution, firstly we make a plan how to find velocity of B. Point B belongs to slider 4 and moves with it. At the same location, there is also a point B3, which we consider as the instant footprint of B on link 3. Now we want to relate point B of slider 4 to its footprint on link 3. So velocity of B can be written as velocity of B with respect to its footprint B3 plus the velocity of the footprint. Then we can relate B3 to point A because both of them belong to link 3. Therefore, velocity of B3 is velocity of B3 with respect to A plus velocity of A. Here is the plan, and now let's perform it starting from velocity of point B3. As mentioned, we relate B3 to point A. Velocity of point A has been given. And we bring it to the diagram starting from OV. Next, velocity of B3 with respect to A. Since both B3 and A belong to the same rigid body, this relative velocity can be described as the angular velocity of that rigid body, omega 3, which is given, times the distance AB3. At this magnitude, we draw a vector perpendicular to the line connecting B3 to A. And the direction of the vector should be in agreement with the direction of omega 3. Then we bring it to the diagram and put it at the head of VA. So, velocity of B3 is the summation of velocity of B3 with respect to A and velocity of A. After drawing, we can measure for magnitude and direction. Now that we have velocity of B3, let's use it for velocity of point B. This is how we relate them. Velocity of B is written as velocity of B with respect to its footprint, B3, plus the velocity of the footprint. Velocity of B3 we already obtained. The relative velocity of the slider along the link has been given. And we bring it to the diagram at the head of VB3. Then, the absolute velocity of B is the summation of the relative velocity of B with respect to B3 and velocity of B3, which we draw and measure. Just a few remarks. Remark number 1, absolute velocities, such as velocity of A, velocity of B3, and velocity of B. They start from OV. But relative velocities start from their references. For example, velocity of B3 with respect to A follows velocity of A, and velocity of B with respect to B3 continues velocity of B3. Remark number 2, we could directly relate velocity of B to velocity of A by considering velocity of B as the summation of velocity of B with respect to B3, velocity of B3 with respect to A, and velocity of A. It's like canceling out B3 with B3 and A with A, resulting in B, which is in alignment with the other side. Let's make a quick summary of what we have learned. As we discussed, between any 2 points in space, we can make such a relation. It says, the velocity of any point can be written as its velocity relative to a reference point, plus the velocity of that reference point. Then the relation could be extended for a system of multiple points. For example, velocity of B with respect to A can be started from velocity of B with respect to M, then M with respect to N, and then N with respect to P, and finally P with respect to A. If the points belong to the same rigid body, then the relative velocity is perpendicular to the line connecting the points. And its magnitude is obtained from the angular velocity of the rigid body times the distance between the points. For the points from different rigid bodies, we reviewed a typical case where a pin belonging to a rigid body has to move along a trajectory located in another body. Then the velocity of the pin can be described as its velocity relative to its footprint on the trajectory plus the velocity of the footprint. And the direction of the relative velocity is parallel to the trajectory.